Welcome. In this presentation, we will learn how to design an HDFS cluster that scales, performs, and remains reliable. Our main objective is to allocate resources wisely so the file system can handle growth, speed, and failure. Key drivers include projected data growth. Imagine 50 terabytes added every year, target throughput and latency, compliance needs such as replication or erasure coding, and, of course, budget constraints. Keep these forces in mind as we move through each design choice. First, analyze your workloads. Batch jobs like MapReduce or Spark consume large, sequential reads and writes. Interactive engines Hive, LLAP or Presto demand low latency, mixed access. Real-time flows from Kafka land and HDFS continuously. Ask, is the cluster mostly read-heavy or write-heavy? Are I/O pattern sequential or random? Answering these questions sets the stage for every sizing calculation that follows. Next, examine the 3 V's: volume, velocity, and variety. For volume, remember replication or erasure coding overhead. 1 petabyte of raw data stored with triple replication suddenly becomes 3 petabytes on disk. Velocity measures ingestion rate, perhaps 1 terabyte every hour. Variety captures file size distribution. Many small files hurt name node memory, while very large files influence block size decisions. HDFS stays safe by copying or encoding data. The default replication factor is 3. That gives strong durability, but triples capacity. For coded data, erasure coding can cut storage almost in half while keeping redundancy. Protect metadata 2. Run name nodes in active standby mode with journal nodes recording every edit so a failover is automatic and fast. Capacity planning is more than guesswork. Use a formula. Raw storage equals usable capacity multiplied by the replication factor, then divided by 1 minus overhead. For example, 500 terabytes required times replication of 3 divided by 0.75 after subtracting 25% overhead yields roughly 2 petabytes of raw disks. Size the machines that hold the disks. A good rule of thumb is 1 CPU core for every 2 to 4 disks on a data node and 64 to 128 gigabytes of RAM. Name node memory scales with metadata, about 1 gigabyte of heap per million blocks. Journal nodes are modest, 2 cores and 8 gigabytes of RAM keep the edit log durable. Network bandwidth is your cluster's circulatory system. Provide at least 10 gigabit Ethernet for small clusters, move to 25 or 40 when nodes exceed 50. Cross-rack uplinks should be at least twice as fast as intra-rack links. Adopt rack-aware replication and consider a spine and leaf topology for predictable east-west traffic. Choose commodity, not exotic, hardware. Use JBOD with 8 to 12 terabyte hard drives for data. Add SSD cache for metadata drives for the name node. Dual socket CPU with 8 to 16 cores, balance cost and throughput. Memory 64 to 128 gigs per data node. And never forget redundant 10 gig switches. Scale out deliberately. Add nodes in batches of 3 to 5 so block placement stays balanced. Separate hot SSD tiers from colder HDD pools and, when using YRN, isolate compute from storage if workloads demand it. In the cloud, enable auto-scaling on-premise. Design racks for quick hot swap expansion. Tune for health. Pick a block size, 256 megabytes for large sequential files, 128 megabytes for mixed loads. Bundle tiny objects into HR archives or store them in HBase. Reserve free space with the DFS data node do. Reserve setting, monitor failed disks and decommission nodes gracefully to keep replicas intact. Let's work a concrete example. You need 1 petabyte of usable space with triple replication and 25% overhead. What capacity required is roughly 4 petabytes. That translates to 40 data nodes, each holding 100 terabytes. The name node heap should be 48 gigabytes, and every rack gets 2 redundant 10 gig links. Validate your design with vendor or open source tools. Cloudera and others offer sizing calculators. Use HDFS admin report to verify capacity and replica counts, then stress test with test DFS IO for both writes and reads. Tune parameters such as DFS replication, DFS block size, and the JVM heap until throughput meets targets. To wrap up, plan holistically storage, compute, and network together. Start small with a pilot cluster at 10 to 20% to final scale. Iterate, monitor, benchmark, and adjust as data grows. Your next steps are to build a prototype, run load tests, and move confidently into production deployment. Thank you for listening, and good luck with your HDFS journey.